Good afternoon. In this occasion, our team, we're going to do a short presentation about separately excited synchronous motor with a rotary transformer for every vehicle application. First, a short introduction. Today, with resonance price spikes and consequent uncertainty in supplying rare air magnetics, have directed attention to machine topologies that eliminate or reduce array content. Some researchers have tried on several occasions to address this issue. A topology with such reluctance engines was recently attempted, so it is highly nonlinear features. All these designs, however, suffer from low torque density due to the low energy of array magnets. Compared to array magnets, on the other hand, the dismagnetization of variable magnets, especially at low temperature, is always a preoccupation. However, the potential and torque densities are still lower than lab or array machines' conventional EP. In order to mitigate these problems, a no-contrary rotary transformer was used, which is designed and developed to excite the rotor coil. Instead of the radial air gap, an axial air gap rotary transformer has been designed. We can talk about the first part of the article, the EN design of SE-SM. First, the SE-SM is designed to match or set the torque and power performance of the Chevrolet Volt engine. The active mentions the inner diameter of the rotor, the stator or air or diameter of the stator, and the length on the battery. This table is possible to observe the motor design requirements and design parameters. And now this figure shows the final geometry of the optimized design. Now it's possible to see the machine and the optimal design of the geometry. The EN design is optimized for maximum torque and specific power, efficient and optimized time torque ripple requirements. Torque ripple is optimized by adjusting three design parameters. It is possible to see in this figure when RO and RL are the radius of the top and bottom top teeth, respectively. For a uniform airspace, both RO and RL would have the same radius as the outer radius of the rotor, but the top. And now we can talk about the design of file power converter and rotating transformer. It is important to understand that in the applications, SE-SM field winding power requirements imposed to the design of an FPC with a speed power of 5 kilowatts. This output power allows fields and provides an extra torque that is necessary, for example, in vehicles passing maneuvers. Now, it is important to understand that this image is about a converter. This converter is digitally controlled by a slave processor to the traction engine. The NCP issues the current field commands to the FPC processor through a separable interface, SPA. The FPC reports the current and health status of the estimate field on the same SPA bus. Now we can talk about the rotary transformer. This transformer was designed to fit into the final latch area on the engine store, so minimal additional space is added to the total length of the transmission. The transformer core is built with high temperature ferrites, and the windings are made of high temperature polymer laminate material. It is important to understand that the work was carried out using an optimization method.
Figure 5 shows the actual halogen design. High power required electrical component are a DV cooler. ATF is used for cooling the transformer for an awaiting. IV simulation experiment tool of the SESN, a SPC experimental result. The SPC performs including transformer and rectifies under load and minimum input voltage. It shows in figure 6 the simulated efficiency has been caused well with the measurements in the same design and efficiency greater than 92% is achieved. Being electrical machine simulation, Table 3 presents the result of the SCS and Torres simulation and a comparison with the PM engine with the SES design. As indicated in the table, a similar Torres performance is achieved. The design engine figure A shows the test apparatus and mounting drive. Figure 9 the measurement retroelectric for of the engine as a function of the fuel current. The saturation of nuclei, the current is visible in the graph. The reduced ENS wave for a field current of liquids as in figure 10, but ENS immediately the assist harmony result from guarding function. The positive contribution of the monitor is achieved with the passive dead current of the D-axis. Mature and Torres flow map are shown in figure 11 for a fuel current of 5 and for a castrol of 90, a more than 90 as a test speed a year maximum Torres is reached figure 11.
Simulation and experimental results. In the figure, it shows that peak torque is rated for a positive control angle as opposed to the normal behavior, where the torque is usually higher for the positive current of the D-axis. At a higher field current, the static maps are skewed to the right. This is mainly due to the saturation effect. The torque speed curve developed for the engine is present in the figure. In the figure, illustrates the torque speed curve of the PM engine. As we can see, the SEMS is able to significantly increase the torque and power compared to equivalent IPM engine. Compared to an IPM engine, the SEMS is working better at a speed about 56,000 revolutions per minute. Below that speed, the PM engine is generally more efficient than the SEMS in Table 4. Compare the measured efficiency of the sim with the reference EPM engine for several key operation points for a hybrid application. The result of the thermal simulation of the SEMS is present in the figure. For several demanding work cycles, winding 1 and 2 represent the temperatures of the stator, winding 2 of the work localization, and winding R represent the winding temperature of the rotor. The coolant temperature in the simulation is 19 degrees Celsius. Conclusions. The development engine has excellent efficiency at high speed and super pace and IPM machines. At lower speed, the IPM machine is more efficient. For applications that require high duty cycles of high speed operation, this engine can be great option with compromise efficiency, higher power and torque, and the complete removal of RE magnetic materials. The SEMS drive system has the drawback of an added cost to the rotating transformer and the power converter. However, this developed eliminated price and supply uncertainties of the permanent RE magnets, which is a major concern for the automotive industry. Thank you very much.